Now previously we were given v of 0 equals 20 centimeters per second and x of 0 equals 0. This gave us the two simultaneous equations we used to solve for a and theta naught. Again, omega was regarded as known. It is 5 radians per second for this whole set of problems, and easily calculated if this is a pendulum, but just from the length of the pendulum, square root of g over L. Okay. Now, we have a situation now where x of 0 equals 3 centimeters, v of 0 equals 20 centimeters per second. What's that mean? Well, we give it a 20 centimeter per second velocity, but it's not at the origin anymore, not at the equilibrium position. It's 3 centimeters out from equilibrium, and we give it that 20 centimeter per second bump. Okay? So, how does that work? Well, it works out in a fairly straightforward manner, except the angle calculations get a little more involved. So as we'll see how that works. Okay, so we know x of 0 is 3 centimeters. So that since x equals a cosine of omega t plus theta naught, a cosine of theta naught has to equal 3 centimeters. X of 0, plug in 0, we just end up with the theta naught in here. So we have a cosine theta naught equals 3 centimeters. And that might be a little hard to read. Let me darken that a bit. Okay, again, a cosine of theta naught is going to be 3 centimeters since x of 0 equals 3 centimeters. V of 0 equals 20 centimeters. Remember that V is obtained by taking the derivative of the x function, the derivative with respect to t, and we get negative omega a sine omega t plus theta naught. If we plug in t equals 0, we just have negative omega a sine of theta naught. And so that v of 0 is negative omega a sine of theta naught, and that has to equal 20 centimeters per second. So now we have two simultaneous equations with the unknowns a and theta naught. How do we solve these equations? Well, good suggestion came from the class. Let's divide one equation by the other. So the left-hand side of this equation divided by the left-hand side of this equation will give us a sine of theta naught over cosine of theta naught, which is going to be like a tangent of theta naught. So anticipating that that's better than dividing this side by this side and getting a cotangent, having to reverse that if we want to use the calculator to find our angle. We have an arctangent button. We don't have an arccotangent button. We want to get a tangent here. Okay, so we do a sine over cosine, meaning we divide this equation by this equation. The left-hand side is going to be negative omega a sine theta naught from here, divided by the a cosine theta naught from here. The right-hand side is going to be, well, 20 centimeters per second from this equation, and 3 centimeters from this equation. Now, I have divided by omega, and that shouldn't be there until the next step, because the omega is still over here. So I'm going to fix that, and then we'll move on. Okay, now the equation reads correctly. Then we divide this out. The a divides the a, leaving us a negative omega sine theta over cosine theta naught, sine theta naught over cosine theta naught, which is just a negative omega times the tangent of theta naught. But then we go ahead and divide by the negative omega over here to get the omega in the denominator and the negative sign. And we're going to then get 20 over 3, because this is 20 over 3, and it's centimeters per second over centimeters. That's going to leave us a second to the negative 1, a reciprocal second. And again, our omega is going to be in the denominator. So that's a very straightforward solution. Let's see what we do with that. Okay, we have tangent of theta naught is negative 20 over 3, and 20 over 3 omega, reciprocal seconds. Meaning that theta is going to be the inverse tangent of negative 20 over 3 omega, reciprocal seconds. Let's bring that back a second. If tangent of theta naught equals this, then theta naught is the inverse tangent of that. So here we have it. Theta is the inverse tangent of our right-hand side. which means that since x of t excuse me, I was looking for what I thought was written there. Since x of 0 is a cosine of theta naught, which equals 3 centimeters, and we've solved this equation now to get theta naught equals negative 20 over 3 omega reciprocal seconds, the arctangent of negative 20 over 3 omega reciprocal seconds. We can take that theta naught and put it back in here. And what we get is x of 0 equals a times the cosine of, remember that's theta naught when x equals 0, theta naught being this. So there's our a cosine theta naught, and that has to equal 3 centimeters since that's our x of 0. So we now have this equation, meaning then that a, our amplitude, is 3 centimeters over the cosine of the inverse tangent of negative 20 over 3 omega reciprocal seconds, which is, of course, negative 20 over 3 I'm sorry, negative 20 over 3 omega, and let me fix that. Okay, I would have picked up a lot of transition on the board. I was using the previous value of omega, the 2.5 radian per second, which was based on the 160 centimeter length rather than the 40 centimeter length, a couple of problems earlier. So I had to make some corrections, and actually the numbers came out a lot nicer. Omega is 5 radians per second. That was the square root of g over L for L equals 40 centimeters. So that this negative 20 over 3 omega reciprocal seconds, the numbers are 3 times 5, which is 15. Divide that into 20. Well, 20 over 15 is 4/3. It's negative. So we have the inverse tangent of negative 4/3. The radian per second and the reciprocal second go together to give us simply radians. And we end up then with the inverse tangent of negative 4/3. Again, an angle expressed without units is automatically in radians. If we want it to be degrees, we have to specify degrees. If we want it to be revolutions, we have to specify revolutions, etc. So we have an angle of negative 4/3, and that simply comes from omega equals 5 radians per second. Just plug into this, and that's exactly what you get. You get negative 4/3 radian, but we don't have to write down the radian because that is the default unit of an angle. Now, how do we get the cosine of the inverse tangent of negative 4/3? How in the world do we do that? Well, we draw a picture. We draw a triangle indicating the angle whose tangent is negative 4/3. The angle whose tangent is negative 4/3 can be represented by a triangle with a negative 4 on this side and a 3 on this side, because again the tangent is defined in terms of the circular model as the y component divided by the x component. Now that doesn't look like a negative y component. It should actually be drawn upside down if we want to think of it on the reference circle or on the circular model with respect to standard XY coordinate system. But it really doesn't matter as long as our side opposite the angle is negative 4 and our side adjacent to the angle is 3, we have a good picture. This angle will then be the angle whose tangent is negative 4/3. That is, this angle will be the inverse tangent of negative 4/3. The cosine of this angle, the cosine of the inverse tangent of negative 4/3, is then the cosine of this angle. And the cosine of this angle is this side divided by this side. Okay. So the cosine of the angle is 3/5, 3 over 5. The negative 4 is over here on this side. The negative sign doesn't affect this or this. The cosine of the inverse tangent of negative 4/3 therefore is 3/5 or 0.6. I'll leave it in the 3/5 form. So we replace the cosine of the inverse tangent of negative 4/3 with 3/5. 3 centimeters divided by 3/5 is 5 centimeters. So the amplitude of this motion will be 5 centimeters. That is, for this pendulum, if we Just place it out to 3 centimeters, give it a 20 centimeter per second velocity. It's going to go out to an amplitude of 5 centimeters before swinging back. And we haven't done the graph, but I think I can erase this and give you the graph. Actually, this is related to this, so I need to talk about this a little bit. We'll do that in the next video.